Hello there, guys. I hope all is well with you. Probably by this time, you all have adopted to our staycation mode. Well, here we are. Amidst the health crisis, we are still strong and dedicated to learn. I guess it's the Education 4.0, where learners are digitally connected and learning is self paced. So, it's me, Rosanna, and today I am sharing with you my assigned topic in real analysis, which is construction of real numbers. Let's begin. Allow me to start by showing you this quotation. You may pause for a minute and think about it. Well, just like what Dr. Arellano mentioned last time, when you study real analysis, what seemed familiar before all of a sudden becomes strange and novel. We think we may already know what real numbers are, but do we really? So let's get into amnesia mode and forget about what we know regarding real numbers for just a short while. Our topic is construction of real numbers. And remember, Chronicler said, God created integers, the rest was made by man. So previously, as a child, what we know as introduction to the concept of numbers is the set of natural numbers, or counting numbers. Then, as we grow older, we know about zero, hence we have whole numbers. Then, not so long after that, suddenly we know about negatives and positives because we have the concept of debt, deficit in the real world. But I think we learn about integers simultaneously with rationals because people share. We share everything: food, money, and time. However, man seemed restless and continues to think. As man learns new things, it leads to another thing or it produces something new. Hence, the set of integers expands further. We have q. Rationals extends the set of integers. In the first two videos provided by ma'am, we should know by now that integers has an ordering property. That is, it has an arithmetic order. Just to recall, an order is a relation that describes things between two quantities. It basically means it satisfies trichotomy and transitivity. Now, if there's an ordering property for integers, does q have order as well? What do you think? If you answered yes, you are correct. Q has arithmetic order also. This means it satisfies trichotomy and transitivity as well. But the question is, why is there a need to construct real numbers? I mean, what made men construct real numbers? Recall the equation x squared equals 2. The equation x squared equals 2 has no solution in the rational numbers because there's no rational number that satisfies this equation. Only numbers that gets super close. In the properties of rationals, this equation had been proven to have no solution. That means Q is not large enough to contain solutions to certain equations such as x squared equals 2. So, how can we further extend our number system to be able to handle all of these cases? Before we proceed to construction of real numbers, let's remember these properties because our construction of the set of real numbers will be based on this. So first, Q extends the set of integers. Q has arithmetic order, which implies that it satisfies trichotomy and transitivity. And it solves some problems. Only some, not all. Knowing all of this about Q, then what's next? We know that Q has order just like Z. That is, we know Q is a field because it satisfies all actions needed to become a field. And what are these actions? So we have 2, addition and multiplication. However, it's somehow not complete, so we need to extend Q. That means we need a new set to complete Q. And that would be R. R is the completion of Q, making it a complete ordered field. So what do you mean by the completion of Q? We can illustrate this by using a number line. So we know already that Q has order just like Z. It satisfies trichotomy and transitivity. Imagine a number line with integers. Then, in between are rationals. However, there seems to be small gaps. What are these gaps? One of the gaps is the solution to the equation x squared equals 2. But where do we get such equation in the first place? Already in the ancient world, it was known that there exist numbers representing a length in geometry which is not representable as a rational number. Say, in a right triangle whose legs measures 1 unit each, we know for a fact that the hypotenuse is square root of 2. But square root of 2 is not rational. These irrational numbers are the gaps on the continuous number line which are not filled by rationals. This already gives us an intuitive concept of completeness. When the real number line is complete, this means that there are no such gaps which are not covered by real numbers. So here are your irrational numbers. Now, what does it mean to construct real numbers? We want a construction that only depends on things we've already defined. We based it on the properties of Q. So if we go back to our number line, any ideas on how we might get to the fact that there are gaps here in the number line? If we look at these rationals here, so maybe x squared equals 2 does not have a solution in Q. So how can we further extend our number system to be able to handle all of these cases? Well, we could choose to define such a number by calling it, say, square root of 2 like we are already familiar with. But like I said, forget about what we learned in school. Even so, that wouldn't be the entirety of real numbers. The approach should be different. We need to try a different approach to construct the complete set of real numbers. The approach that we'll take was conceptualized by a German mathematician, Richard Dedekind, who came up with this method of describing real numbers while he was teaching calculus. Imagine that you have a number line, but it only contains rational numbers. Dedekind noticed that he could cut the rational numbers at a particular number, and by doing so, partition the rational numbers into 2 non-empty sets. A lower set containing all the rational numbers that were strictly less than that number, and an upper set containing all of the rational numbers that are greater than or equal to that number. So if there is no solution for x squared equals 2, it might be worthwhile then to look at another possibility. Let's consider looking at the following set. The set A, which is consisting of all x in Q, such that x squared is less than 2. So we will use this inequality in this kind of partition of the rational numbers. This is nowadays what we call as the Dedekind cut. So let's consider constructing real numbers using this possibility. The Dedekind cuts are actually the key that let us finally construct the real numbers. It says every non-empty subset has the least upper bound. Sometimes this is called the supremum property or completeness property. Recall that we've already said that there's no solution to the underlying equation x squared equals 2 in the rational numbers. So the solution x to this equation must be irrational. Let's consider set A such that x squared is less than 2 for all x in Q. According to Dedekind, every non-empty subset has the least upper bound. The problem is, in Q, there may not be a least upper bound for this equation. In your number line, whatever irrational number x happens to be, the lower set of our Dedekind cut contains all the rational numbers that are less than x. Then, the upper set contains all the rational numbers that are greater than or equal to x. But there is no rational number whose square is 2. So everything in the upper set is actually strictly greater than x. With this idea, we've essentially found that there's a hole in the rational numbers where we made this cut. And this will happen in every rational number that we can come up with. Making a Dedekind cut at that number will partition the rationals into those that are strictly less than that number and those that are strictly greater than that number. Now, let's have the definition or a notion for an upper bound. Suppose S is an ordered set and E is a subset of S. If there exists beta in S such that for all x in E, x is less than or equal to beta, we say E is bounded above and call B an upper bound for E. In this particular case, S is the set of rational numbers while E is the set A containing all x such that x squared is less than 2. If nothing from E can exceed beta from set S, then set E is bounded above. This simply means that you are asking if there is a number on that set that is bigger than everything. If there is, then it's an upper bound. This is the notion of an upper bound. To define lower bound, simply change less than equal to greater than equal to. Let's have an example. If this is our number line, and this is where our cut is, we can say that 2 is an upper bound. But how do we know that it is an upper bound for A? Any idea? Well, by definition, if set S is the set of rational numbers, and set E is the set A containing all x such that x squared is less than 2, then 2 is an upper bound for A, since there isn't a number x in A that is greater than 2. That is, all numbers from this set is strictly less than 2. So 2 is an upper bound for A. How about 3 halves? 3 halves is an upper bound for A as well. But how do we know that it is an upper bound for A? Here is a short proof. Proof by contradiction. Suppose 3 halves is not an upper bound for A. then there exists x in A such that x is greater than 3 halves. This means x squared is greater than 3 halves squared, which implies x squared equals 9/4. So then, x is not in A, for set A is the set of all x containing x squared less than 2, which is a contradiction. Therefore, 3 halves is an upper bound for A. Now that we have the notion of an upper bound, let's talk about least upper bound, or LUB. What is a least upper bound? Well, it has to be two things. First, it must be an upper bound, and among all the upper bounds, it is the least. By formal definition, if there exists alpha in S, such that, first, alpha is an upper bound of E, and if there exists gamma which is less than alpha, this implies that gamma is not an upper bound of E. Then alpha is called the least upper bound of E, or we say alpha is the sup E or supremum of E. Here is an example. Let's say S is the set of rational numbers. Then consider E to be the set whose elements are 1/2, 1, and 2. Does this have a supremum? What is it? You are correct. The supremum, the sup E or the supremum of E is 2. 2 is an upper bound of E. It is the least upper bound because if there exists gamma less than 2, then 2 is greater than gamma, which implies gamma is not an upper bound. Do finite collection of things have supremum? You are correct. It is the biggest in the collection, sort of the last one on the number line. Finite sets have a supremum. How about infinite collection of things? Do they have supremum? Let's have an example. Consider E to be the set of rational numbers that are negative. Do this have a supremum? You may pause the video for a minute to think about it. Answer. Well, you are correct. Sup E or supremum of E is equal to 0. But why? Well, again, based on definition, every number x in set E is less than 0, and 0 is the least among all upper bounds found in Q. Let's have another example. How about the set of rationals? Does this have a least upper bound? What is sup E? Well, sup E does not exist. This implies set E is unbounded above. For set E, which is the set of rational numbers, sup E or supremum of E is equal to positive infinity. There is no least upper bound. How about x squared is less than 2? If our set A is the set of all x such that x squared is less than 2, does this have a supremum in Q? What is your answer? Well, you are correct. The supremum of A does not exist. There is no supremum in Q. This leads us to the construction of real numbers. Now that we have laid out our concepts about Dedekind cuts and supremums, we can finally construct real numbers. The theorem says R is an ordered field with the least upper bound property, and R contains Q as a subfield. So we will construct R by only involving concepts on rationals. There are 3 things we are going to show about our construction of R. First, it has a least upper bound property. Second, it is an ordered field. And third, it extends Q. Let's start with the least upper bound property. A set S has the least upper bound, or a set S satisfies the completeness axiom if every non-empty subset of S that has an upper bound also has a least upper bound, or a supremum in S. The set must be non-empty. This is important since if the set is empty, how will there be a supremum? So it must contain something. Dedekind's idea was to think about the real numbers as just being some collection of rationals that are specified in some sense by this cut. Our task is to construct the real numbers in a way that only involves the things we have defined before, which are rationals. We are going to make a cut right here, and we're going to say that everything to the left is a collection of rationals that will be called a cut. A cut has three properties. A cut alpha is a subset of Q such that, first, this collection alpha is non-trivial, implying alpha is not equal to phi and alpha is not equal to the rational set of rational numbers. This means the collection must not be empty, but not everything. For the second property, this will be a collection that is closed downwards. If P is an element of alpha and little q is an element of the set of rational numbers, and q is less than P, then q is an element of alpha. This means it is closed downwards or closed to the left. The third property, on the other hand, this collection does not have, in some sense, a biggest member. If P is an element of alpha, then P is less than R for some R element of alpha. Let's have examples on determining whether a set is a cut or not. First, is set A a cut? What do you think? You are correct. No, because it failed property number 2. It is not closed downward. How about alpha, which is a set of rationals that are negative? You are correct. It is a cut. It satisfies all properties. What about this set? Let beta be the set of all rationals in Q such that R is less than or equal to 2. Is this a cut? No, it is not a cut. It fails property number 3. It has a biggest member. So again, we have to remember, for a set to be a cut, it has to satisfy the 3 properties. It has to be non-trivial, it must be closed downwards, and there is no largest member. In the construction of real numbers, our focus will be on sets that are cuts. This sets will be the set of all real numbers. So let's proceed and continue on the construction of real numbers. Let R be the set of real numbers such that it contains alpha, where alpha is a cut with structure. This means it has to have order and it has arithmetic in the field operation. By now, we already know what a cut is, so let's discuss structure. If a set has structure, it must have order. So what is order? Say alpha is less than beta if and only if alpha is a subset of beta, but not equal. So what does this mean? If we have two cuts, say alpha and beta, or collection of rationals to the left of some number, alpha is less than beta if and only if alpha is properly contained in beta but not equal. This is an order because it satisfies trichotomy and transitivity. What about the field operations? What operations are involved? So we have addition. Just like your set of rationals, we also have addition for real numbers. Addition is defined as alpha plus beta equals the set of all little r plus little s, such that r is in alpha and s is in beta. Is this set a cut? So again, for it to be a cut, it must satisfy the three properties of being a cut. Let's check. First, it is non-trivial because it is non-empty set. Alpha and beta are non-empty sets. Second, is it closed downwards? Suppose little p is in alpha plus beta, and little p is equal to little r plus little s, where r is in beta and s is in alpha. And q is less than p, where q must be in alpha plus beta. Since q is less than p, then q is less than r plus s. So q minus s is less than r. Since r is in alpha, then we say q minus s is in alpha. Then we can say q is equal to q minus s plus s, where q minus s is in alpha and s is in beta. Therefore, alpha plus beta is closed downwards. And for the last property, this set alpha plus beta has no largest number. Therefore, it is a cut. And then also, we would want to include axioms for addition. And what are these axioms? We have 5. First, we have closure. Since we have shown that it is a cut, it means it is a collection of rationals. The operation is closed. Second, commutative. Since alpha plus beta equals little r plus little s, where r and s are rationals, and addition is commutative for rationals. Number 3, associativity. Associativity for real numbers follows that of rationals. Additive identity. Suppose we use the symbol 0 star to denote the collection of all negative rationals, so that alpha plus 0 star equals alpha. 0 star are actually cuts, and these are actually sets of rationals. This implies that alpha plus 0 star is contained on alpha, and also alpha is contained in alpha plus 0 star. This means if I take something in this alpha and I add something from 0 star, which is the set of negative rationals, the sum will still be in alpha, because when you add a negative to some number in alpha, it will only get smaller because it's closed downwards. In the same manner, if I pick something in alpha, it will be the sum of something in alpha and a negative rational, because there is no largest number. For the 5th axiom, we have additive inverse. We need to show that alpha plus beta equals 0 star, which means beta will be the set of all rationals such that there is a number r greater than 0, such that negative p minus r is no longer in alpha. So if addition is the sum process, it's an addition of cuts. What about multiplication? For multiplication, if alpha and beta are in positive reals, or the ones that are bigger than 0, then alpha beta is defined to be the set of all little p such that p is less than rs for some r in alpha, s in beta, and rs greater than 0. This is the case for positive rationals. For negative numbers, basically, you make them positive, you multiply, and then negate as needed. Then, for multiplicative identity, we let 1 star be the set of all rationals such that these rationals are strictly less than 1. So all of this satisfies the multiplication axioms such as closure, commutativity, associativity, multiplicative identity, which in this case is 1 star, and multiplicative inverse. So now, to finish our construction of real numbers, let's answer one last question. How do we get the supremum of a bunch of cuts, which is actually the set of real numbers? That is, if we have a collection of cuts, what's the set that's going to contain them all? Because it's bigger, but it's the smallest thing that contains them all. What do you think? Well, we will take the union of all the cuts. So, given a set of cuts A, let gamma be the union of all alpha such that alpha is in A. Then, gamma is a cut, and gamma would be the supremum of A. In summary, we say that R is simply a collection of cuts defined by Richard Dedekind, and R completes Q because somehow it fills in the gap where Q does not exist. And R has structure because it has order and it has field operations. So thank you very much for listening, and I hope you learned something. Bye.